Um, okay, so today and in the next lecture, we are gonna cover best policy identification. So we are moving from the bandit model to the more general Markov decision process model. The main difference is that we have the notion of state now. So in the bandit case, you can select an arm and observe a reward, and what you selected in the basic model doesn't influence anything else. Here we have the notion of state. So there is a system with some state, and every time you take an action, this action will affect the state of the system. The state will evolve according to some transition function, to some dynamics. And based on these dynamics, you will observe an evolution of the state. So upon selecting an action, you will observe the next state that we call st+1, and you will also observe a reward. The reward here, it's basically the same thing that we also had in the bandit case. And the goal will be to try to maximize the total reward that we collect from the system. So for MDPs, we have the state space, which is the set of possible states. We have the action space, which is the set of possible actions that you can take. Then we have the transition function that we denote by P. This is a distribution over states conditioned on the current state and action that you took. And then we also have the reward function. The reward function maps state action pairs to values in 0, 1 for simplicity. And we will denote by RT the reward that we observe at time step t, which is function of the state and action that we observed at time t. Then we define a policy to be a collection of sampling rules. And we say that the policy is stationary in Markov if the sampling rules are the same for all time steps, and if the policy only depends on the last state that you observed. So a Markov policy will choose the action based only on the last state. It will not choose the state based on the entire history of data. And here the history, it's a bit different from the bandit case. In the bandit case, we started with an action. Here with MDPs, we start with an initial state. And then you take an action, you observe a reward, and you observe the next state, and so on. So here the definition of history is a little different. So we define the value of a policy as the expected total discounted reward. So here we define V pi of S to be the value of a policy pi in state S. And this is the expected value of this sum of discounted rewards. Here gamma is the discount factor. It's a value in 0, 1. And since the rewards are bounded in 0, 1, you can show that this expected value is always upper bounded by 1 divided 1 minus gamma, because it's a geometric series. So the boundedness, it's required to ensure that the value is well defined, even though we can admit unbounded rewards, but then we need some condition on the moments of the reward. And this applies only for stochastic rewards. But here we're only focusing on deterministic rewards. And for deterministic rewards, we make the assumption of boundedness. So like in the bandit case, the main goal will be to identify what is the best policy. So the best policy is the one that maximizes the value in each state. So it's the one that maximizes the expected total discounted reward. From this value function, we can also write what is the Q function. So we can define the Q function in state S action A to be the immediate reward that you observe plus the average value at the next step discounted by gamma. So this is the classical recursive decomposition of the Q value. And a similar decomposition also applies for the value here. And we also have the equality that the value in S of a policy pi, it's also equal to the sum over actions of the probability of taking that action in state S times the Q function evaluated in SA. Then we can also define what is the best policy. As I said before, it's the policy that maximizes the value. It needs to maximize the value in every state, and we can write it in this way. So a policy pi star, it's optimal if it satisfies this equality here. So if when we take a supremum or all possible Markov policies, then this difference in the infinity norm is equal to 0. And the infinity norm is with respect to all the states that we have. And here we make the assumption that the state space is finite. And also the action space is finite. So the idea also in the proof that we will look at today is to see the values as vectors in the state space. So these are values, these are vectors in R to the power of the size of the state space. So each entry of this vector represents one value for a specific state. Another important property for this type of MDPs is that the optimal policy is deterministic. We might have multiple optimal policies. What's interesting is that the set of MDPs with multiple optimal policies have as Lebesgue measured 0. This is something that we will not prove. But basically, this says that if you have a continuous set of MDPs and you uniformly sample from this set, then with probability 0, you will pick an MDP with more than one optimal policy. So we indicate by pi star the optimal policy, and we indicate by V star the optimal value. And given the definition of optimal value, we can also define what is the suboptimality gap in SA. So for an action A, we can ask ourselves how far we are from optimality. And this is measured by this quantity here. So obviously, if action A is optimal, this quantity will be 0. If action A is not optimal, this quantity measures how far we are from optimality. And we can also define what is the minimum suboptimality gap. And this quantity will be non-zero if there is only one unique optimal policy. Okay. So in the following, we will make the assumption that pi star is unique for simplicity. And we also make the assumption that the MDP we are considering is a communicating MDP. So communicating MDPs are nice because of this property here that says that between two states, there is always a policy, a deterministic policy, that allows you to go between these two states with some probability in a certain number of steps. So here we have that the probability under this policy of going from S to S prime in these steps is bigger than 0 for some value of t. So if you imagine a graph, it means that the graph is well connected so that between two nodes in the graph, you can always find a way to go between these two nodes. Then another important concept is the concept of stationarity. And to introduce this concept, I want to use the definition of the number of visits. So it is NTSA. It's the number of times we picked action A in state S. So in other words, I will also say the number of visits to the state action pair SA. So now the question is, can we characterize what is this quantity here? What is the average number of visits to SA? So if we take the limit as t equals to infinity of NTSA divided by t, does this limit exist? Is it finite? Does it oscillate? If this limit exists and is finite, we say that pi induces a stationary distribution d pi over S times A, so the state action space. And this quantity converges to this d pi. So this d pi represents how frequently you will visit SA at infinity. And we can also show that at stationarity, this condition needs to hold. These are the stationarity equations. So whenever you have a stationary distribution, what you have is that the stationary distribution is an eigenvector for the transition function associated to the eigenvalue 1. Why are we looking at stationarity, and why do we care about this? It's because in the lower bound that we will derive, this constraint will appear. As we let the confidence delta go to 0, so as we make our lower bound, as we take more confidence in the result of our testing problem, this stationarity constraint will appear in the lower bound, which makes sense because as we let the parameter delta go to 0, it means that we want to be more confident, and in a sense, time is going to infinity because you will need more and more samples to approach that level of confidence. And as you approach infinity, then stationarity at some point will start to kick in, and that will be the main regime of the lower bound. So we can guarantee, for example, stationarity if we assume that the Markov chain induced by the policy is aperiodic and irreducible. So here we define p pi to be the associated transition function of policy pi. So it's the Markov chain induced by pi, and it's simply defined in this way for a stochastic Markov policy. So if we make these two assumptions, we can guarantee that the distribution, the stationary distribution, exists and it's unique. But apart from this, we will not touch this assumption. We will not use this anymore in the rest of the 2 lectures. So what we are going to do today is try to derive just the lower bound. And the problem of the lower bound here is that the set of alternative models is a non-convex set. So when we are trying to take the infimum over alternative models, what happens is that this set is non-convex, and so we have some problems at simplifying the optimization problem. And the main idea will be to try to find a relaxation and try to make the problem convex. So we will enlarge the set of possible alternative models. By doing so, we are not finding a lower bound anymore, but we are finding an upper bound. Because of that, we cannot claim to be optimal anymore, but the main idea is to try to find something that is sufficiently close to the lower bound. So as we will see at the end, it's a good result, even though it's not the best that we can get, but the technique is quite involved. So we need several technical lemmas, and maybe it will be possible to improve it in the future, but for now, this is the best we have. Yes, so let's start by deriving the lower bound first. And we need first another lemma before we show the lower bound. And this lemma, it's about the navigation constraints. So how do the number of visits evolve over time? So for example, let's consider the number of visits to state S at time tau. So this is equal to the indicator function that we visited that state at the initial step plus, and here we need to write a sum of indicator functions. What is the way we are going to write it? It's in this way. So we are going to write sum over S prime A prime, sum from n equal to 2 up to tau, indicator function that in Sn minus 1 we were in S prime, An minus 1 we were in A prime, and Sn is equal to S. So if tau is equal to 1, we have only this term here. If tau is equal to 2, we have this term, and then here this sum is from 2 to 2. So we have a sum, we have only one sum over all state action pairs. And this indicator function is simply capturing the event that we were in some state action pair S prime A prime, and then we visited S. So why are we writing this number of visits to state S in this way? Simply because in the lower bound, we will show that the navigation constraints will tend in the limit to this equation. And sorry, in this equation here, it's sum over S prime A prime. So this sum over S prime of this quantity will be exactly sum over S prime A prime of the transition function time the stationary distribution, which is what we want to, which is what we want in the end. So we need to rewrite the number, this quantity here in this way, so that in the limit it will converge to the stationary distribution. So now let me introduce another variable just for simplicity. So we are gonna write W of S prime A prime K to be the number so this random variable here will be the number of times, no, sorry. It will represent the state that we observed after the KF visit to S prime A prime. So we can rewrite the previous equation. And what I want to do is to replace this inner sum and write it in terms of K. So it will be from K equal to 1 up to n t minus 1 S prime A prime. So it will be from the first time we visit S prime A prime up to the last time we visited S prime A prime of indicator function of W S prime A prime K being equal to S. So I just rewrote the previous equation because now when we take expectation, we can apply Wald's lemma. So now take expectation and apply Wald's lemma. And so we obtain that the expected number of visits to state S, it's equal to the probability. Sorry, here it's 1 equal to S. So the probability that the first state is equal to S plus sum over S prime A prime, but the expected value of this inner sum times the indicator, we can apply Watt's lemma, and it simply becomes the expected number of visits to S prime A prime up to tau minus 1 times the probability. So this indicator function will, on average, it's the probability of visiting state S from S prime A prime. So to conclude, what we want now is to show that the difference is, yeah, S1 is the first state that you see. So if this state is equal to the state S that you're considering, then you will increment the number of visits of 1, right? But then when you take the average, this becomes average of an indicator, which is a probability. What we want to show in the end is that the difference between the expected number of visits minus this kind of quantity is always upper bounded by 1 in absolute value. And we will use this in the lower bound. So what I'm going to do now is do plus minus sum over S prime A prime of the expected value of n tau S prime A prime times probability of S given S prime A prime. So I added this quantity because here I have a shift of minus 1, but I want tau. So I can bring to the right-hand side the plus term. And this will be equal to probability, S1 being equal to S. And here we are doing a difference between this quantity and this quantity here. So we have minus sum over S prime A prime probability that in tau minus 1, we are in S prime A prime. Sorry, probability. No, indicator, sorry. With the expected value. So now we can take the absolute value. This probability is in 0, 1. Also this quantity, it's in 0, 1 because it's expected value of an indicator, so it's a probability. And when you sum over S prime A prime, it's also in 0, 1. So since we have a difference, we have shown that this the left-hand side, it's upper bounded by 1. in absolute value. And here, I think I also forgot that there was this term appearing here. Yeah. Okay, so for the lower bound, we're going to use this result. And I will not derive the entire lower bound because the idea is basically the same as in the bandit case. So we can move on and directly go towards the end. So in the lower bound, we have some overaction of n t s a KL. It will be the KL divergence between the transition function of the true model and the transition function of an alternative model. And I will write it in this way to indicate the transition in SA. This is a distribution over the next state, okay? Why don't we have the rewards? Because we assume the rewards to be deterministic. So only the transitions are unknown. If the rewards are deterministic, in a sense, it means that you already know what are the rewards. And also, if the rewards are deterministic, there is no room for an alternative model. And this is lower bounded by the Bernoulli-Kerr divergence in delta 1 minus delta. So these lower bounds, it's exactly from the, is similar to the bandit case. What changes is that this quantity here, we need to constrain it. We need to constrain it because we are following what the NDP shows us. So we are following on a trajectory of an MDP. And we are constrained to what we see from the NDP. We cannot just sample any state that we want. We can sample actions, yes, how we want, but then the next state that we see, we are constrained by the transition function. So when we optimize here over alternative models, and I will define what is this set of alternatives in a second, and then we will also optimize over the sampling rate, we also need to take into account that NT of SA needs to follow a similar equation as this one. Okay. So what we will do is impose this constraint here, because this constraint also includes the navigation constraint, this one. So we are gonna define WSA to be equal to NTSA in expectation divided by expected value. Also here we have an expectation, expected value of tau, and here should be, it's tau, not t. And so when we take the supremum over the W's are constrained by this inequality here. So concretely, we have supremum over W's, infimum over M prime that belongs to a set of alternatives, sum over SA, WSA, KL, PSA, P prime SA, lower bounded by D delta Y minus delta, and the W are subject to this constraint here. So what is that constraint saying? So, the constraint, it's this one. Less than 1. Okay, so we can replace this expected number of pulls, the expected number of visits of SA by using this change of variable. So this will become expected value of tau times WSA. Similar also for this quantity, it will become expected value of tau times WS prime A prime. But then we can divide both quantities, both end sides, by expected value of tau. And so we obtain this inequality here. And now what we need to see is that the expected sample complexity will basically tend to infinity as we let delta go to 0. And when this happens, this right-hand side converges to 0, which means that this quantity needs to be equal to this quantity. So as delta tends to 0, we have that the Bernoulli-Kell divergence converges to infinity according to log 1 over delta. And so at the very end, what we have is that expected value of tau divided by log 1 over delta as we take the limit as delta goes to 0. It's lower bounded by a characteristic time T star of M, where T star of M inverse, it's the solution to this optimization problem. Subject to the stationarity constraint. So something that probably I didn't say before. So in the navigation constraint here, we had the expected number of visits of state S. This is also equal to sum over action of the expected number of visits of SA, which is what I used here. Then basically what I did here was to divide by the sample complexity. But then when we divide the sample complexity by log 1 over delta and we let delta go to 0, the sample complexity is basically also diverging at a certain rate. But here on the right-hand side, this quantity will tend to 0 because we have a constant divided by sample complexity. And so if this inequality is equal to 0, it means that this is equal to 0. And we obtain this constraint, which is exactly the constraint that I showed you before for the stationary distribution. So these are the stationarity constraints. So what the lower bound is telling us is that the exploration as delta goes to 0 will be it will be only affected by how we explore as stationarity. What happens before doesn't matter so much. And this is a nice result. The problem is we only know what happens as stationarity. We don't know what happens before. We are not sure. We are not even sure if the algorithm that we can design using this lower bound will be optimal before stationarity. So there are like downsides to this approach, and it will be interesting to understand how the sample complexity behaves before stationarity. Can we avoid letting delta go to 0? Can we work with moderate regimes of the confidence? These are all questions that we still don't know how to answer. Yes, I still need to define what is this set of alternatives. So the set of alternatives depends also on what is our objective. And our objective is to try to estimate what is the best policy. So the set of alternatives is defined as a set of alternatives MDPs, such that the optimal policy in M is not optimal in M prime. So this is a very informal definition, but we can also rewrite it in a different way. So it's the set of alternative MDPs where there exists a state action pair such that policy pi star in M prime evaluated in SA is bigger than the value of pi star in S evaluated always for this MDP. And here this action needs to be different from the action that it's taken by pi star. So the reason why we can write this, it's because if there is an action different from the action taken by pi star, such that the value in that action is larger than the value of the action taken by pi star, then it means that you can improve the policy. So you could find another policy, let's call it P prime, such that in this particular state, it's equal to A, so it is action A, and everywhere else, it's simply equal to pi star of S prime. So this is a policy that improves on pi star in this alternative MDP. And this policy is different from pi star. So we already showed from this little example that M prime is an alternative model because pi star is not optimal in M prime. We can already find another policy that improves on pi star in M prime. And now the issue is that, yes, we can rewrite it in this way, but the problem is this is a non-convex set. And the reason why it's a non-convex set, it's because the value, I will not do the proof. This will take too much time, but in general, the value function of a policy can be written in matrix form in this way, where this is the transition function induced by the policy, the one I showed you before. This is the identity matrix. This is the discount factor. This is the reward vector. So this is a matrix that multiplies the reward vector, and we obtain a vector of values. Because of the inverse, so we know from Cramer rule that the inverse can also be written as the adjudicate matrix of I minus gamma p pi divided by the determinant of I minus gamma p pi. And we know that these two quantities are both polynomials. Those will be polynomials in P. And so basically the value function is a rational function in the transition. And it's very easy to come up with examples where you have two alternative models, but then if you take the convex combination of these two models, results in a model that has the same optimal policy as the original model. And this comes from the non-convexity that we see here in P. So this is non-convex in P in general. Okay, so what we will do now is to try to relax this alternative set. So we will try to find a condition that is a bit less tight, which means that the set of alternatives will enlarge. So it will also include models that are not alternatives. But at least we get something that is convex. And yeah, we stop for now. Let's take a 5 minutes break. Okay, so let's start again. So what we will do now for the rest of this lecture is just try to derive this relaxation. And I think the idea behind the relaxation is quite nice, and can turn out to be useful also in other situations. So we will, for this reason, I will go over the proof and try to show what are the main ideas. Okay. So we said that the main issue is the non-convexity of the set of alternatives. Because when we look at this optimization problem, in the end, everything else is fine. This constraint is nice. It doesn't pose any issue. The KL is a convex. It's a convex function. So in reality, the only issue comes from the set of alternative models. So we need to find a way to rewrite this inequality in a different way and to enlarge the set of alternatives. So let me rewrite that inequality. So this inequality holds for some state S and action A different from pi star of S. The way we are gonna manipulate this inequality is by making explicit the dependency on the suboptimality gaps. So if you remember, the suboptimality gaps in the original MDP are defined in this way. So it's the difference in value between the value of the optimal policy in S and the value of action A in state S, always in the original MDP. And we also have the minimum gap, defined as the minimum over states, action difference from pi star of S of delta SA. So why do we want the gap? Because intuitively, even from the bandit case, if you remember, the lower bound for Gaussian rewards show a dependency on the gaps. So the idea is, can we make this dependency on the gap explicit also for MDPs? the answer will be yes. And to make it explicit, what we are gonna do is simply we are gonna sum this equation with this inequality. So note that we can simply write delta SA plus value in S of the optimal policy in M prime. It's bigger than Q M prime by star SA plus VM star of S minus QM star of SA. So this inequality is it's exactly the same as the original one, because here this one it's an inequality. So this term is equal to this quantity. So we have not done we have not changed anything. We just added this equation to this inequality. But now we have the gap that appears, which is nice. The other reason why we want to do this is because from this expression that we have on the right-hand side, we will make explicit what is the dependency on the Kähler divergence between P and P prime. So the transition function in the original NDP and the alternative NDP. And this dependency on the Kähler divergence between P and P prime will turn out useful when eventually we will lower bound this KL. Why do we want to lower bound the KL? Because if we lower bound the inverse of the characteristic time, then it becomes an upper bound for the characteristic time, which is what we want. So what we are gonna do now is try to simplify this expression here. So we have difference in value and the difference in the Q values. So let's look at the difference in the Q values. So the difference in the Q values, since the rewards are the same in both NDPs, we have that the rewards will cancel out. So let's see why. So the first quantity is simply equal to reward in S A plus gamma sum over S prime, P prime, S prime, given SA, value in M prime of pi star of S prime, minus the Q value, the optimal Q value in M, but the optimal Q value in M is given by the policy pi star. So here, this is also equal to this. And these two rewards will cancel out because the two MDPs have the same rewards. So we are left with this difference here. Here we have the value in M prime, here we have the value in M. We are gonna do plus minus gamma sum over S prime. And here we want P of P prime of S prime given SA times the value in M of pi star of S. And so we can take the difference between this term and one of these terms. So we get gamma sum over S prime, P prime, S prime given SA times delta V, where delta V, let's write it as dV, where dV, it's simply Vm prime by star minus Vm by star. And the other term will be plus gamma, and I'm gonna write it as dp SA transpose times the volume m of pi star. So here I'm trying to use vector notation. This dv, it's the difference between these two value vectors. And since I'm using vector notation here, I can just write the inner product between P prime in SA. So P prime SA transpose times this vector dv. So this prime SA, it's a vector for me. So basically each value in this vector, it's P prime S prime given SA. And the sum can be written as this inner product. And the same here for this other term, where we are taking the difference between this quantity and this quantity. We will have P prime minus P, which we denote by dP. So dPSA, it's simply the difference between the vectors P prime in SA and P in SA in vector form. So the original inequality becomes gamma P prime SA transpose dV plus gamma dP SA transpose Vm pi star. And then we also add the difference of values, this difference. But what is that difference? It's minus dV. So this was Vm minus Vm prime. dV is defined as Vm prime minus Vm. So we can do minus Es transpose dV. So this is a vector of the canonical basis. This is the one-hot encoding of state S. And in mathematical terms, it's basically a vector of the canonical basis where it's equal to 1 for the dimension associated to state S. So when we take the inner product between ES and dV, this quantity will be equal to the difference in value in state S. And here we have strict inequality. Yeah. And so the final inequality, it's this one. We have gamma P prime SA minus ES, all transpose dV, plus gamma dP SA transpose Vm pi star. So also until now, we didn't really do any change because this is just a chain of equalities. So there is no inequality involved so far. But we can see that from this difference of transition function, we will be able to extract a Kähler divergence of pp prime when we take the absolute value, and also the same here for dv by using order inequality. So what we are going to do now is try to upper bound this quantity and this quantity in absolute value. This will turn out useful later, and it will show the dependency on the KL divergence. So let's start by bounding this simpler term. So just for simplicity, I will write v. So let's try to write as less as possible. So here, I mean, we can simply apply order inequality, right? This will become the difference between P and P prime of SA. But there is a small step we should do first. We need to take advantage that here, this vector is a difference of probability distributions to make the upper bound a bit tighter. So what we can do here to gain advantage of this fact is to subtract a constant value. So let's call this constant mu from the value. And this constant here, you can imagine it as a vector that is constant. And so why does the equality holds? Because since this vector is constant, we have that this inner product here is equal to 0. So we can subtract a constant to obtain something that is a bit more meaningful. And then we apply Holder's inequality. And the constant that we are going to choose will be mu SA. Mu is equal to mu SA, which is equal to the expected value of the next state sampled when we are in SA of the value in M of S prime. So this is the constant we are going to consider. The reason why we choose this constant is also because when you do the value minus this constant and you take the square, then this becomes the variance of the value. We are not gonna show like how the variance appears, but the idea is that instead of doing this Holder inequality the way we'll do it, you can maybe think of applying Cauchy-Schwarz maybe, but we will take a simpler route. So we're simply gonna apply Holder's inequality in this way. We will get the difference in the L1 norm between P and P prime times the infinity norm of V minus mu. And we also know that the L1 norm, it's equal to 1 over 2 total variation. And we also know that the total variation, it's upper bounded by square root of 1 over 2 KL by P square inequality. And so here we can upper bound this term by 2 square root 1 over 2 KL P SA, comma P prime SA times V minus mu infinity. So this will be useful later because we can exploit this the fact that we can now lower bound the KL of P prime by this inner product divided by V minus mu in infinity norm. So we are going to do a similar thing also for the other term now. So the other term was dV. So what is dV? So for simplicity, I will just write V and V prime. So let's consider some state S. So dV evaluated in S, it's Vs minus V prime S, or the reverse, we had V prime minus V. And we are using the same policy. Remember, we are always evaluating for pi star. So this difference is simply R S pi star of S plus gamma sum over S prime, P prime, S prime given SA of V prime S minus R S pi star of S minus here gamma S prime, P prime, S prime given SA B of S. So these two terms will cancel out. So same trick, plus minus. And we want to do plus minus and make the dV term appear. So we're going to do plus minus gamma sum over S prime, or let me write it directly in vector form. P prime SA transpose dV. So we have dV evaluated in S, it's equal to gamma P prime SA transpose. Sorry, here it's just V. So if it's only V here, when we take the difference between this term and this term, we have dV appearing. And then we have plus, and also here it's just P. We have plus gamma P prime SA minus P SA transpose value of V. So I just rewrote everything in vector form. So we can take now the absolute value, apply triangle inequality, and take the maximum over S. So let's take the absolute value and then take the maximum over S. And yeah, there is also another small error here. So this is not actually A, but it's pi star of S, because we are following the policy pi star of S. So here we actually have S pi star of S, V prime of S prime, and also here we have P S prime given S pi star of S, V S prime. The same here, P prime S pi star of S transpose V. So also here we have S pi star of S transpose, and here also we can write the P S pi star of S transpose V. So here, when we are taking the maximum over S, is also taking into account the action. So this quantity, it's also upper bounded by the infinity norm of dV by order inequality. And this quantity here on the left, it's also the infinity norm of dV. So we have just shown that dV in infinity norm is lower bounded by gamma, infinity norm of dV, plus max over S of gamma, absolute value of dp S pi star of S, transpose V. So now we just bring this term to the left-hand side, collect 1 minus gamma, and divide by 1 minus gamma. So that in the end, we have just shown that dV in infinity norm, it's upper bounded by gamma divided by 1 minus gamma, max over S of the absolute value of the inner product between dp in S pi star of S, transpose V. And here we can apply the same trick as before. We can subtract a constant, and the constant we are going to choose in this case is simply this one. So it's the same definition as before. Expected value of S prime when sampled from PS pi star of S of the value in M of pi star in this state S prime. So when we combine everything together now, in the original inequality, we had delta SA. We can take the square already. So what is upper bounded? What is the upper bound here? So the upper bound was the sum of these two terms. We showed an upper bound for dV, an upper bound for this guy. So the upper bound of this term, it's this quantity. We need to take the square. So the square root will disappear. We are left with 1 over 2. Sorry, we are left with 2 times the KL times this difference infinity norm squared. So we have 2 gamma squared KL P SA P prime SA difference in infinity norm. This V is the value in the original MDP under the optimal policy. I will just write V from now on. So this is the upper bound for the for this quantity here. Now we also have the other quantity. When we take the absolute value of this quantity, we can apply again order inequality. So the absolute value of this quantity, let me write it explicitly. So we have something like P prime minus ES transpose dV. So when you take the absolute value, this is upper bounded by the L1 norm of this guy times the infinity norm of dV. This quantity here, it's upper bounded by 2 in L1 norm. And this quantity here, we found the upper bound before. This one here. So we have just shown that this becomes plus 4 because we also need to take the square of this quantity here, gamma squared divided by 1 minus gamma squared times max over S prime of the square of this inner product. Yeah. So this is the upper bound that we have. Now let's go back to the problem of that we had originally. So the original problem was infimum over alternative models, sum over SA of W SA times KL of P SA P prime SA. So because of the way the alternative set can be written, if you remember, it's this equivalent way of rewriting it. Because of this equivalent way, we can also rewrite the infimum as minimum over state action pairs where the action is different from pi star of S, such that this inequality holds. So this is also equal to minimum over S, A different from pi star of S, infimum over models M prime, such that Q M prime pi star of SA, it's bigger than the value in M prime of pi star in S, of the sum of WSA, KL, PSA, P prime SA. And now what we should note is that, well, first of all, let me change this SA because otherwise we confuse with this SA. So maybe we can write S prime, A prime here. So what's interesting is that this constraint is only affecting the pairs SA and all the pairs S prime, pi star, S prime. It's not affecting any other state action pair. It's only affecting those. So because of that, we can simplify the expression here. So we can set the transition function for some of the state action pairs equal to 0, all the state action pairs that do not appear here. So this will become equal to minimum over SA, different from pi star of S infimum over n prime such that this inequality holds of W SA KL PSA P prime SA plus sum over S prime W S prime pi star S prime KL P S prime pi star S prime comma P prime S prime pi star S prime. So this is the first simplification. Now the next thing is to try to use the upper bound that we found on this condition here. So what we want to do now is to try to find a lower bound. Because remember, this is the inverse of the characteristic time. So if we find a lower bound, it will become an upper bound for the original lower bound, which is the direction that we want. We cannot find an upper bound because then it becomes a lower bound for the original characteristic time, which is loose. What we want really to do is to try to find an upper bound of the characteristic time, because that implies that we are doing a bit of over exploration, but at least we know that we are doing the right kind of exploration. So we're exploring, but it's not loose like finding a lower bound of the characteristic time. In that case, you cannot derive guarantees that you're exploring in the right way. So to derive the lower bound, we will try to lower bounds the KL. We know from one of the previous inequalities that we have a lower bound on the KL from this inequality here. But we also want the dependency on the gaps to appear. So we want this gap to appear, right? What we are going to do is a nice trick. We want to understand how much the first term and the second term, each one of these two terms, how much they contribute to this inequality. So let me rewrite it here. So, okay, so the inequality that we had, it's this one. I will write the one without the upper bound for now. So this is the thing that we had that then we upper bounded, right? So we want to understand how much of these two terms contribute to this inequality. It means that we want to find these two coefficients, alpha 1, alpha 2. These are non-negative. And these two coefficients also satisfy this inequality, such that alpha 1 delta SA squared is equal to 2 gamma squared inner product of dp SA and V. And the same for the second term. So here I'm being a bit sloppy with the notation, but it's just to convey the main ideas. So alpha 1 represents basically how much we need to multiply the gap so that we are equal to just the first term. And similarly for alpha 2. So if alpha 2 is equal to 1, it means that the gap squared is equal to this term. So this inequality is always true as long as this quantity is a bit bigger than 0, right? So this second term is the dominant one. So this alpha 1 and alpha 2 basically represents how dominant each one of these two terms are. So now we are gonna plug in the upper bounds that we found before. So alpha 1 delta SA squared, it's bigger than 2 gamma squared. So basically this thing here. So I'm just gonna write PP prime because it's clear that it's NSA times the difference in the infinity norm between V and mu. Also this, I will not write the dependency on the state and the action. There is also a factor 2 that appears, so this is 4 actually. Okay, so we have this term, and we can lower bound the KL. So KL P prime is lower bounded by alpha 1 delta SA squared divided by 4 gamma squared V minus mu infinity. And maybe now it's a bit more clear why we introduce alpha 1, alpha 2, because now we can clearly lower bound the KL in terms of the gap. Before, yes, we were able to find an upper bound here in terms of the KL, but then how can you clearly find an inequality of this kind between the KL and the gap? It's not clear because here you have a sum. So we need a way to make the contribution from each of these two terms more explicit. So we needed to introduce alpha 1 and alpha 2. So now that we can lower bound KL P prime in terms of the gap time alpha 1. And we are going to do the same also for the second term. So the second term, we have alpha 2 delta SA squared. It's equal to 2. We are going to upper bound this quantity. And this quantity is upper bounded by gamma squared divided by 1 minus gamma squared maximum over S prime. And here we have KL. Here we have S prime, pi star of S prime, and so on. I will not write it. And also here the value minus mu. Here the mu, it's always with respect to S prime, pi star of S prime. So now we can try to lower bound the KL, but it's not the right way. So remember what we have. We have this term. This KL can be lower bounded using this inequality that we derived before, which is valid in SA, where A is different from the from pi star of S. But then we also need to lower bound this entire sum. So the way we are going to lower bound this sum is by saying that this sum is lower bounded by the maximum over S prime of W S prime times KL. So we are lower bounding just one term. We are lower bounding the maximum term in this sum. Why are we doing this? Because the inequality that we have here you see there is a maximum over S prime. So we cannot just lower bound each term of that sum. What we're gonna do is just lower bound the maximum term. So here what we are gonna do is multiply and divide by W S prime pi star S prime divided by W S prime pi star of S prime. Then this quantity is also upper bounded by 2 gamma squared divided by 1 minus gamma squared. We have max over S second. Let me write it explicitly so it's clear what's going on. That multiplies max over S prime of KL P S prime pi star S prime. And here we have P prime with the same arguments. That multiplies, let me just write KL PP prime that multiplies the W. And it's this W denominator. So what we did was to split these two terms so that we multiply the KL with the numerator and we multiply the difference here between V and mu. We divide it by the W. And then we can upper bound this quantity by taking the two different maximums. One maximum over this quantity here and another maximum between the KL times the W. So now we know that the maximum term in that sum, so we know that max over S prime KL P S prime pi star S prime P prime S prime pi star S prime, it's lower bounded by alpha 2 delta SA squared divided by max over S second of V minus mu, infinity norm squared. Also here we had the square divided by W. And then we also have the 1 minus gamma squared divided by 2 gamma squared. So we found a lower bound on this KL that multiplies also WS prime pi star S prime. So this quantity is lower bounded by this other quantity. So we are finally ready to lower bound both terms. So this sum will be lower bounded by the maximum quantity in this sum, which is the inequality that we just derived. And the first term means that we can use the lower bound that we derived here. So we have just found that the initial lower bound can be lower bounded. I mean, the initial inverse of the characteristic time can be lower bounded in this way. So we always have this minimum over SA, where A is different from pi star of S. And then we have W SA alpha 1 delta SA squared divided by 4 gamma squared V minus mu infinity. Squared. Yes. And then we have the other term, which becomes plus minimum over S prime of W. Here it's S prime pi star S prime alpha 2 delta SA squared divided by this v minus mu infinity norm. And also here we have 1 minus gamma squared divided by 2 gamma squared. So for simplicity, from now on, I will just write h1 of SA, this first quantity here. And I will write h2 of S prime, the other part. And we are also going to lower bound the delta SA by delta mean, just for simplicity. And probably I forgot to factor 2 somewhere, but I mean, it's just a constant factor. It's not important for now. Probably should be 4, but it's not important, so we can leave it as it is. Okay, so at the end, we have just found this lower bound. Alpha 1 WSA, H1 of SA plus minimum over S prime of alpha 2 W S prime pi star of S prime times H2 S prime. And I also forgot another condition here. We have alpha 1 and alpha 2. We are taking a minimum also over those quantities because we are trying to optimize, right? So remember, what we wanted to do is to separate. We wanted to separate the contribution of these two quantities in this inequality. So we introduced these two parameters, alpha 1, alpha 2, such that alpha 1 plus alpha 2 is bigger than 1. But what we are going to do now is optimize with respect to these parameters. So we make it tight. So we are taking the infimum over alpha 1 plus alpha 2 bigger than 1. But now the infimum over the open set is also equivalent to the infimum over the closure. And since this is a convex problem, the optimal will be attained at alpha 1 plus alpha 2 equal to 1. So on the simplex. And since it will be on the simplex, it also means that alpha I squared will be smaller than alpha I. So we can lower bound the values of alpha by the square. So I'm just doing this because if we don't do this step, then we are gonna get a sort of a trivial solution. But if we take the square, it's gonna look a bit nicer. And so this becomes infimum over alpha that belongs to 0, 1 of alpha. The first quantity here, I will call it x, and this other quantity, I will call it y. So alpha squared x plus y minus alpha squared y. So when we solve this, we can take the first derivative of this quantity. We get 2 alpha x minus 2 1 minus alpha y equal to 0. So alpha x minus 1 plus alpha y equal to 0. Here it's y. So we have that alpha is equal to y divided by y plus x. And when we plug this back, this is also equal to minimum over SA, different from pi star of s, of if you replace the value of alpha, what you get is xy divided by x plus y, which is similar to the results that we obtained in the Gaussian bandit case when we introduced the approximate solution. So now what we're gonna do is just replace the values of xy. This is equal to minimum over SA different from pi star of s of what? WSA, H1SA, minimum over S prime, WS prime pi star S prime, H2 S prime divided by the sum. And so we have just shown that this quantity, it's a lower bound to the characteristic time when we evaluate it in a specific W. So the infimum over alternative models of the sum of the W's times the KL, it's lower bounded by this quantity. This is inverse, so a lower bound for the inverse of the characteristic time, which means that the characteristic time, it's upper bounded by the inverse of this quantity, which is simply max over SA, different from pi star of S, of 1 divided by WSA, H1 of SA, plus max over S prime, 1 over WS prime, pi star of S prime, H2 of S prime. So the gaps were, the H factors were proportional to the gaps. So they were like gap squared divided by this difference of the value with the constant. So we can see that the gaps appear at the denominator. So we get like difference of the value squared divided by WSA, delta SA squared. Here there is a constant plus also the second term that will look similar. And so we have just shown that the sample complexity for this relaxation, basically it's characterized by this infinity norm of this difference between the value and this constant. This is a sort of span of the value. And also it's affected by the gap squared, which is also what we expected given what we have seen in the bandit case. So the last step here is simply to optimize in W. So at the end, you are gonna optimize in W so that you can make it as tight as possible. Of this quantity here. And the W is always constrained to the stationarity constraints. So subject to sum over A of WSA being equal to sum over S prime A prime of P S given S prime A prime W S prime A prime for each S. So yeah, this is the sample complexity result that we're gonna use to derive a design of the algorithm. We are gonna apply exactly the same idea that we applied in the bandit case. So we are going to derive an algorithm that is inspired by this sample complexity result. It's called navigate and stop. The idea is you solve this optimization problem that we just derived. This optimization problem gives you the allocation W star. This W star is computed with respect to some MDP, where we use the empirical estimate of the MDP. And we will also make some changes so that we can guarantee that the MDP is well estimated. And so the W star that we compute eventually will converge to the W star of the true MDP. And asymptotically, we are exploring according to the true optimal exploration. So thank you for attending, and I'll see you on Monday.